A medical test is 99% accurate. You test positive. What is the probability you actually have the disease? Most people say 99%. The real answer is about 9%. This is not a trick. It's Bayes' theorem, and it is the same mathematics that powers every AI system making decisions under uncertainty. Before we can understand Bayes' theorem, we need to be precise about what probability actually means. Flip a fair coin. The probability of heads is 1/2. One way to understand this: if you flip the coin 1,000 times, roughly half will be heads. This is the frequentist view. Probability is the long-run frequency of an event. Watch, as we flip more and more, the fraction of heads converges to exactly 1/2. But there's a deeper interpretation. Suppose I ask you, what is the probability that it will rain tomorrow? You can't flip tomorrow 1,000 times. Here, probability measures your degree of belief, your confidence, given what you currently know. This is the Bayesian view, and it is the foundation of how AI handles uncertainty. Probability is not just counting outcomes, it is a language for reasoning about the unknown. Now here's where things get interesting. Suppose we have two events, A and B. They can overlap. Some outcomes belong to both A and B. Conditional probability asks, if we already know that B happened, what is the probability that A also happened? The key insight is this: when we learn that B happened, our universe of possibilities shrinks. Instead of considering everything, we only consider outcomes inside B. The probability of A given B equals the overlap, P of A intersection B, divided by the total probability of B. And here's something crucial. P of A given B is generally not the same as P of B given A. If you see someone carrying an umbrella, there's a decent chance it's raining, but if it's raining, there's a very high chance they have an umbrella. The direction of conditioning matters, and confusing the two is the most common probability mistake. This asymmetry is exactly what Bayes' theorem resolves. Now let's derive the most important formula in probability theory. We just saw that P of A given B equals P of A intersection B, divided by P of B. But we can write the same intersection from the other side. P of A intersection B also equals P of B given A times P of A. Substitute this into our formula and something remarkable appears. P of A given B equals P of B given A times P of A divided by P of B. This is Bayes' theorem. Let's give each piece a name. P of A given B is the posterior, what we believe after seeing the evidence. P of B given A is the likelihood, how probable the evidence is if our hypothesis is true. P of A is the prior, what we believe before seeing any evidence. And P of B is the evidence, the total probability of what we observed. This single equation is an engine for updating beliefs. You start with a prior belief, observe evidence, and out comes an updated posterior belief. Let's return to our medical test and work through it step by step. Imagine 10,000 people get tested. The disease is rare. It affects 0.1% of the population. That means 10 people actually have the disease, and 9,990 are healthy. Now we test the 10 sick people. The test is 99% accurate, so about 10 of them correctly test positive. These are true positives. Next, we test the 9,990 healthy people. The test incorrectly flags 1% of them. That's about 100 false positives. So out of everyone who tested positive, about 110 people, only 10 actually have the disease. 10 out of 110 is about 9%. This is Bayes' theorem in action. The prior, the prevalence of 0.1%, is so low that even a very accurate test produces far more false alarms than true detections. The prior matters enormously. Let's see Bayes' theorem build a real AI system, one you use every day without realizing it. An email arrives. Congratulations, you won free money. Is this spam? A naive Bayes classifier looks at each word and asks, how likely is this word in a spam email versus a legitimate one? The word free appears in 60% of spam, but only 5% of legitimate emails. One appears in 40% of spam, but just 1% of real emails. Money, 50% spam, 3% legitimate. Now comes the naive part. We assume these words appear independently, so we can simply multiply the probabilities together. The spam score is the prior times all the word probabilities. The ham score is calculated the same way. After normalization, the classifier is 99.97% confident this is spam. Why is it called naive? Because words are not truly independent. Free and money tend to appear together. But despite this simplification, naive Bayes works remarkably well in practice and was the backbone of email spam filters for decades. Now let's watch Bayes' theorem in continuous motion. Suppose you find a coin and wonder, is it fair? Before flipping it, you have no information. Your belief about the probability of heads is completely flat. Any value from 0 to 1 is equally plausible. This is your prior distribution. You flip the coin 10 times and get 7 heads, 3 tails. Watch what happens to your belief. The flat prior concentrates. It now peaks around 0.7. You're starting to believe the coin might be slightly biased toward heads. Now flip 100 times, 70 heads, 30 tails. The distribution becomes razor sharp. With more evidence, your uncertainty shrinks. Let's see this in 3 dimensions. The height of this surface represents how likely each parameter value is, and it concentrates into a sharp peak as evidence accumulates. Evidence sculpts belief. That is the essence of Bayesian thinking. Now let's connect this to AI. When we train a neural network, we're searching for the best parameters, the theta that maximizes the posterior probability. This is called maximum a posteriori estimation, or MAP. The MAP estimate maximizes the likelihood times the prior. In log form, we maximize the log likelihood plus the log prior. Here's the beautiful connection. If the prior is a Gaussian, a bell curve centered at 0, then the log prior becomes negative theta squared. That's L2 regularization, also known as weight decay. If the prior is a Laplace distribution, a sharp peak at 0, the log prior becomes negative absolute theta. That's L1 regularization, which drives parameters exactly to 0. Every time you train a neural network with weight decay, you are performing Bayesian inference. You're saying, I believe a priori that my parameters should be small. And Bayesian optimization, which finds the best hyperparameters for your model, uses a prior over functions to intelligently explore the search space, updating its belief about which settings work best after each experiment. Bayes is everywhere in modern AI. In episode 1, we learned how AI represents the world as vectors and matrices. In episode 2, we learned how AI improves by descending through a mathematical landscape. Today, we learned how AI handles uncertainty with a 250-year-old equation that converts prior belief plus evidence into updated knowledge. In episode 4, we'll discover how AI learns from its mistakes. Backpropagation, the algorithm that taught billions of parameters to work together.